So today we will be discussing about glass, which you all know is an amorphous material. Now an example of a glass which is or a glass type material is AS60, AC60. This is a room temperature malleable glass. Now coming to the mechanical properties of a glass, it is brittle, or you can say it is fragile, having very low toughness, and you may also call it as stiff, a high value of resilience. And apart from the mechanical properties, what's interesting about glass is its optical properties. So it can be transparent, or it can be even translucent depending upon the refractive index, and that in turn depends upon the material used in the glass. And coming to its electrical properties, it is insulating, and it is also chemically inert. Okay, so that makes it durable, where chemical reactions are very severe. Now, a very good example of a glass or a practical application of glass is lithium ion conducting glass ceramics. And it is in short written as LICGC. And what's characteristics of these type of glass are it has got a solid state electrolyte, or a separator. You can and it is mainly the next generation lithium ion battery and other electrochemical devices will actually are or will be using this LICGC. Other applications of not only glass but any amorphous material for that matter It can be used as a glass cover. Then it can be used as a camera lens. TFT displays. Dielectrics. And circuit packaging. And these are the normal uses. There are some extraordinary uses of amorphous materials. So these are basically, you can say, metallic gas case. A phase change memory device. And also in solid state batteries. Now, when we say an amorphous material, what do we actually mean? When we say a material is amorphous, it means that it is a metastable solid with no long range ordered atomic number. So, first of all, it's a metastable and no long range order. So these two characteristics make a material as an amorphous. Now if you plot the energy versus the structure, so it's not exactly a plot in that sense, but it actually depicts the different size and the different shape of the glass and their particular use. So usually it's in this fashion. If we plot the structure with the energy and this state, this is the metastable glassy state. Metastable glassy, and this is actually the thermodynamically stable crystalline phase. So it is basically what this diagram is telling is that the atoms in the amorphous state can rearrange themselves to form a more stable state, and it also gives a lot of energy. Okay, so this is the diagram which actually shows the atomic rearrangement is very much happening in the case of an amorphous alloy, giving it a transition from the two different states. Now, coming to the structure, basically this amorphous, or it basically comes in the shape of an oxide. So basically it's AU2O3. This is a 2D compound. And how do we actually understand whether it is in crystalline state or the amorphous state? So basically what happens is in the crystalline state there are basically the arrangement is very much homogeneous. For example, if you consider the atoms sitting here like this, the oxygen atoms in the open branch or in the branches. So every branch have its own oxygen atom, and if there are the E atoms, which can be anything, is at the corners. If this pattern is maintained throughout the crystal, then we can call it a A2O3 crystal. However, if no such fixed geometrical pattern is maintained, for example, in this case, we are drawing a hexagon. So instead of hexagon, we draw, say, any irregular shape like this. And again put the atoms in their places, then the structure that we get is, this is now the AO2O3 glass. So a transition can occur with the simple movement of atoms. So what is the difference between these two? First of all, you can see that there is no long range order, so long range order is disrupted, and the structure, the advantage of this amorphous type of material is that since there is no the properties are mainly isotropic in nature. So for example, structural symmetry, due to the structural symmetry, it actually due to the lack of symmetry, it is usually isotropic. So we'll put it here, it's an isotropic. And the reason behind is that it lacks symmetry. Lack of symmetry is making isotropic. Now, other features of glass is basically you can call it another way as a continuous atomic network. And the absence of small angle scattering is present, so I can say that there is an absence of small angle scattering. And it is due to the this is due to the fact that there are no microvoids present in the glass. So that is the reason it is there is no small angle diffraction taking place in the glass, and the size is, since it is an amorphous, so that makes it size of the order of 10 angstrom. So this Dirac equation is not valid here. Okay, so no Dirac equation. So this Dirac equation, it is basically your it says that the slit size is equal to uh, k beta by cos theta. Okay, this is the Division equation. K is any constant, beta is the full width of maxima, and cos theta is the angle where the refraction is taking place, and this is your slit size. So it depends upon this bandwidth or full width of maxima. Now, since in a amorphous material, if you take an XRD, they have a shape like this. If it is an amorphous material, so they actually show a hump. So this hump has got a, so this beta will be here. It should be k lambda. I'm extremely sorry. So it's not, this is the equation, wrong equation. So not the right equation. So it says that d is equal to k lambda by beta cos theta. This is the Debye-Scherrer equation. Lambda is the wavelength of the X-ray, which is usually of the order of 1.54 angstrom if you're using a copper X-ray. K is called the shape factor. Now, for calculations, we usually assume that the structure is spherical in shape. So that now might not be the case. Slides might be of different shapes. So since we assume it because it is having the lowest surface area and it is supposed to be the most stable shape, so for assuming or considering all the crystallite size of this shape, we had to introduce a shape factor which is called K, and the value is very close to 1 or 0.9 something. This beta is your full width of maxima. So it means that if we have a plot like this, so for this peak, if you deconvolute, or if you just observe carefully or put it through mathematical equations, you will find that is a bell-shaped Gaussian plot, and the bandwidth or the full width half maxima is beta. And from the equation you can see that a lower crystallite size implies, or rather I should put it, a higher value of full width of maxima implies that the crystallite size are very low. So in the amorphous material we basically get a very big hump. So we get a hump like this, or even more than that. So indicates that this has got a very big full width maxima, and so automatically the crystallite size is reduced. So as I have already told you, it's around 10 angstrom. It's next to nothing, so we don't consider any crystallinity to be existing in the case of an amorphous material. Also, there are no very small crystallite size, so we don't calculate the crystal, we don't consider any crystals in amorphous material. Okay, and or you can, so the glass is not able to, it's not a collection of extremely small crystallites, and basically it's a homogeneous system. Okay, so since I am telling that the crystallite size is small, so it may be implied that it is a collection of extremely small crystallites, but that is not the case. The whole material is covered by very low crystals, which are less than or around 10 angstrom. So that doesn't make it any crystals. So it is basically amorphous material. Uh, the most common or the glass for that term, what we actually mean is when we are talking about silica or SiO2. This is the glass that we all know of. Now, coming to the structure of SiO2, SiO2 structure is based upon a model called random network model. Of silica. So it is basically a radial distribution function. So if you put here R in Armstrong and you put here the distribution function, so it is actually, so let's put it as FR. So it's actually like this. So these peaks indicate the different bonds that usually take place. So this lowest one is your SiO2. There might be other bonds, like that might be OO bonds, or there can be a silicon-silicon bond as well. So these three peaks indicate the three different types of bonds that are taking place. Now, coming to the structure, this SiO is basically a tetrahedron. So let's try it. So there is a silicon atom at the center, and there are 4 atoms surrounding it. So it's the silicon atom is at the top, and it's like an umbrella type of thing. This is how the structure looks. This is the structure looks, and next is the formation of a glass. So basically we have 3 states: solid, liquid, and glass. So if you suddenly allow the material in the liquid state to suddenly quench, means suddenly cool, then there is a chance of formation of a glass. This is valid for metals also, so that's how we make metal glass. And if you allow a slow heating process, or annealing for that matter, it will first of all it will relieve the material from stress, and also it will form a solid, which happens to be mainly in the crystalline state. Now, thermodynamically, if you plot the enthalpy or heat of formation for that matter versus the temperature, so you get a plot like this. So this is your crystal state, so you can call it a crystal. Sorry. And this part is supposed to be the liquid or the molten state. Okay, let's concentrate on the liquid and the solid. Now these parts can be interchanged. So if it is a liquid, so if you reduce the temperature, so it basically quenching. This sharp line indicates there is a quenching taking place. So it will solidify and it will form a crystal. Similarly, on increasing the temperature from a crystal, you can suddenly go to a liquid. Okay, so this phase transformation from the liquid glass to the solid, this is a first order phase transformation. And so another interesting fact is that the processes are reversible in nature. It's not that if you convert a liquid to a crystal, it cannot be melted back into the liquid. So there is always possibility of and reversible process. Now, apart from, now as we see that we need to cool the liquid to a crystal, so the cooling process is important, and due to this, we again come to another parameter or another term for that matter. It's called a supercooled liquid. There is a difference between a glassy state and a supercooled liquid state. A supercooled liquid state, it will transform to a glassy state. It can transform to a glassy state when crystallization is kinetically suppressed. So if we could suppress the crystallization process, if you could suppress it, then from the glassy state it can go to the or rather from the supercooled state or from a crystalline state it could come to a glassy or amorphous state. So it's also called a glass transition. Now if you plot another potential versus temperature diagram for glass, and now for the consideration of supercooled liquid, so it actually will show a plot like this. Okay, so this is this is the original plot they actually thought. So in the last diagram we actually have drawn this. Now, but usually it's not exactly as sharp as it looks. Okay, there are some other states as well. So this is your liquid state, reversible process, and so if you draw a tangent to it, and from a tangent from here, so intersection of these two tangents will give you the glass transition temperature. And after melting, if this is the melting temperature Tm, so after that what you get is your supercooled liquid. So this is your glass transition, and this is your supercooled liquid. So this is H and this is T.